Hello to my 3 viewers. 5 viewers. Hello. Gonna wait until we have, excuse me, about 30 viewers, and then I will begin. How am I doing today? I have a bit of a headache because of the smoke. I went for a run yesterday and I thought the air quality was better than it was, and then in the evening I got a headache afterwards. After my run, I got a headache, and then it just kind of hasn't gone away. What I what kind of fascinates me is, have you seen these pictures from like San Francisco where it looks, the sky is completely red? And I'm curious, like, what are the conditions? Like, where does the fire have to be? Where does the sun have to be? Um, how thick is the smoke to create those conditions where it looks like that? Um, because I really thought yesterday we might have one of those red sky events, but it didn't happen. Yeah, the all the assignments are going to be on Canvas. I'm going to wait maybe another minute or two while the number of viewers goes up. I think the one nice thing about it is that the smoke at least makes it a little bit cooler. Yeah, it's definitely, Ian. It's definitely about um, how the sunlight interacts with the particles. Yeah, I don't know. It might be the size of the particles. Um, the reason that the sunset looks red is because in the sunset, the light has to travel through more atmosphere before it hits your eyes. That's what makes the sunset redder than when the sun is up above. Um, so I don't know if it's the exact same effect. All right, so I think I'm going to get started. Um, yeah, so generally what happens is, um, if you have a beam of light, which is white light, if you have white light traveling through a cloud or something, then the blue light tends to get scattered out of the beam. So if this is the beam of light, it's going like this, then blue light will hit a particle and it'll get scattered perpendicularly. So the blue light goes perpendicular to the beam. And so what's left behind is red light that keeps going straight and makes it to your eyes. Um, So generally it's going to get redder the further the beam travels. Okay, so I'm going to get started. And Amir, I see your question. We'll go over that during the Zoom room. Okay, so let me switch to my document camera. The first thing I want to remind you guys is that we have an assignment that's due tonight at 11:59 p.m. That's the first assignment. All right, so what we're going to talk about today is all focused on slope. So what if we have a graph, y versus x graph? Okay. So we have a y versus x graph, and it has a line. And on that line are 2 points. You have x1, comma y1, and x2, comma y2. All right. If I do this, that'll be better. I'm trying to make my contrast a little bit better. Let me see if I turn the slide on if it makes it even better. Trying to adjust my camera, my document camera, so you can see a little bit more clearly. Okay, so if we want to calculate the slope, then we could use the point slope formula, which is y2 minus y1 over x2 minus x1. Okay, so that's slope. However, if we think about this in terms of physics language, x1, y1, that's like your initial position, and x2, comma y2, that's like your final position. So I could rewrite it as y final minus y initial over x final minus x initial. Okay. We could go further because final minus initial is just delta. So we could rewrite the slope as delta y over delta x. However, in physics, we oftentimes do not have y on the vertical axis and x on the horizontal axis. So I will actually call these the vertical axis and the horizontal axis. All right? Because very rarely are we going to have y and x. Okay? So we can write the slope as change in whatever is on the vertical axis over change in whatever is on the horizontal axis. Okay? So this is an expression for the slope that is going to be useful for us today. All right? Today's lesson is all about slope. So, you might remember from the last lesson, we did an example where it was a number line, and I had woken up at position x equals 0, and then I walked to position x equals 7 in 4 seconds, and then I stayed put for 3 seconds, and then I walked over to x equals minus 3 in 2 seconds. Okay, so that is how I drew it on Friday, or on Tuesday, excuse me. we would like to translate this into what's called a position time graph. Okay? Also known as an XT graph. So a position time graph means that we have on the vertical axis, we have the position measured in meters. And on the horizontal axis, we have the time measured in seconds. Okay? So this is very standard in physics and actually in all of science. When you have a graph, you want to put the variable for the quantity and then the units that you're using for that variable in parentheses next to it. So on the vertical axis, I have x. X is the variable for position. Parentheses, the units I'm using to measure it, which are meters. And then on the horizontal axis, I have t, which is the variable for time, and then parentheses, seconds, the units for time. Okay, so if I want to translate this motion here into a position time graph, here's what I would do. At time 0, I am at position 0. So that's where I started. And then it took me 4 seconds to get to position 7 meters. So position 7 meters is up here. So that might be position 7. And then that took me 4 seconds. 1, 2, 3, 4. So here is the point representing that at 4 seconds I was at position 7 meters. And I'm going to connect those by a line. Okay? Then, for 3 seconds, I stayed at position 7. So my position number is going to stay put at 7 for an additional 3 seconds. So 1, 2, 3. So between 4 seconds and 7 seconds, I'm remaining at position 3. Okay? And then for 2 seconds, I go all the way from position 7 to position -3 that is down here. And that took 2 seconds. So from 7, I go 2 seconds beyond that to 9 seconds. And I go all the way down like that. So that is how that graph. So this is an alternative depiction of the motion. All right? And this depiction is more useful than that. Okay, it's less confusing. So what we want to figure out is what is the meaning of slope? Okay, slope is change in vertical divided by change in horizontal, coming from this formula right here. So what is on the vertical axis? We have x, position. What do we have on the horizontal axis? That is time. Okay? So slope is change in position divided by change in time, which is velocity. Okay? So our first key fact for today's lesson is that velocity is the same thing as the slope of a position time graph. Okay, so that is our first key fact for today. So, what if I asked you a question like this? What if I said, what is the instantaneous velocity at 2 seconds? All right. Well, what I would do is I would go to 2 seconds, and I notice that 2 seconds, this graph is made up out of 3 line segments, right? But if I look at 2 seconds, 2 seconds corresponds to this first line segment. So really what I'm asking is, what is the slope of the first segment? Okay? So I ask for the velocity at 2 seconds, and I would take this line segment and I would look at the two endpoints and I would calculate the slope between those 2 points. Okay? If you want to know what is the velocity at 6 seconds, then that would be, I go to 6 seconds and I find the slope of that line, that's a flat line, so it has a slope of 0. So that one's pretty easy, 0 meters per second. Similarly, if I said what is the velocity at 8 seconds, 8 seconds corresponds to this third line segment, so I would take these 2 points and calculate the slope between those 2 points. Okay? I would never ask you to find the velocity at like 4 seconds because it's kind of undefined. It's in the this is sort of in the transition between the two line segments, so the velocity isn't defined. If the slope is positive, that means you're moving in the forward direction. If the slope is 0, that means you're at rest. If the slope is negative, it means you're moving in the negative direction. So this is the meaning of slope in a position time graph. Okay? The next question we want to answer is, how is acceleration represented in a position time graph? Well, the definition of acceleration is change in velocity over change in time. Okay? And velocity is slope. So that means that the slope is changing. Okay? So what does a graph look like if its slope is changing? It means you have one slope, and then later on you have another slope, and then you have another slope, and then you have another slope, and then you have another slope. So you get a curve. It's no longer a straight line, but it's a curve. Okay? So our second key fact for today is that acceleration is equal to the bendiness of the graph. If the graph is the bendiness of a position time graph is acceleration. All right? So what if I have a position time graph that looks like this? Maybe it goes something that looks like that. All right. So if we look at this first segment from here to here, then that's a straight line. That's not bendy. That's not bendy. So what that means is that there's no acceleration. It's a constant velocity for that first segment. Okay? But then at this time, it becomes bendy. So that instant right there, that is when the acceleration starts. So it starts accelerating. Okay? And then we can see at this point right here, it becomes a straight line again. So it goes from bendy to a straight line. So that would be the time where it stops accelerating. Okay? So there you have it. I would never ask you to actually calculate the acceleration from a position time graph. Okay? I will ask you to calculate the velocity, because that's just the slope. But what I'll ask you about acceleration is I'll simply say, is it accelerating or not? Okay? And for example, if I gave you, is it accelerating at this time? You would say yes, because the portion of the graph corresponding to that time is bendy. Okay? And if I asked you, is it accelerating at this time? You would say no, because it's a straight line for that point. Okay? There's a really excellent question, which is, wouldn't that represent a deceleration? We can see that the slope goes from steep to not as steep. So the slope went from large velocity to a smaller velocity. So that would represent slowing down. I prefer to not use the term deceleration. I prefer to use the terms speeding up and slowing down. I think that's more descriptive. Okay? Because your acceleration can be positive or negative. So I would say this is a negative acceleration, but the particle is slowing down. Let me give you another example of a position time graph. What if you were skydiving? So you start out with a really large position, you're elevated, right? And you jump out of the airplane. What's going to happen is you're going to start to accelerate. So you're going to go, we're going to have a bendy graph. It's going to be bendy. By the way, a nice way to tell if the graph is bendy is if you have any piece of paper or something like that, you can hold it up against and you can see how it's bendy. So you compare it to a straight line. But if you go skydiving, what you find is that you accelerate towards the ground at first, but then you actually stop accelerating. So the graph becomes a straight line. I know that's a straight line because I'm comparing a piece of paper to it and I can see that it's straight. So why does that happen? Well, as you're falling through the Earth's atmosphere, and the faster you fall, the harder the Earth's atmosphere is pushing against you. That's called air resistance or drag. So as you build up speed, the drag builds up as well. And eventually the drag is so great that you can't speed up anymore. And so you reach what is called terminal velocity. Or terminal speed, okay? So the terminal speed of a human skydiving is about 120 miles per hour, okay? You can adjust the terminal velocity by changing your shape. Terminal velocity depends on shape. So if you went into if you're falling like this, like a flying squirrel kind of pose, then your terminal velocity is going to be less. Okay? You're not going to fall as quickly. If you go into a pencil pose, your terminal velocity is going to be greater. All right? Your terminal velocity also depends on the atmosphere. Okay? In particular, if there was no atmosphere, there would be no terminal velocity. There's an excellent question. Does weight affect your terminal velocity? Yes, it does. So basically what determines your terminal velocity is your shape, the atmosphere, how thick is the atmosphere, and your weight. So it's basically a balance between gravity pulling you down and air resistance pushing up on you, okay? So if there was no atmosphere, this graph would just continue to bend, all right? If there was a really thick atmosphere, this graph would level off. It might level off right there. And so you reach a smaller terminal velocity. So yeah, this graph can contain so much information about the atmosphere, about the person who's falling. It's really pretty cool. All right. So that's one type of graph. It's called a position time graph. We're going to talk about a second kind of graph, which is a velocity time graph. Which is also known as a VT graph. So let's take, a VT graph has velocity measured in meters per second on the vertical axis, and it has time on the horizontal axis. So how could we express this motion as a velocity time graph? Well, what was the velocity for the first 4 seconds? For the first 4 seconds, we traveled 7 meters in 4 seconds. So that first velocity is 7 over 4 meters per second. Okay? So what that means is that for those first 4 seconds, we had a velocity of 7/4, which is 1.75 meters per second. So the velocity was steady at 1.75 for the first 4 seconds. Okay? Then what happens at 4 seconds? The graph goes flat and the velocity becomes 0. So if we were to represent this as a velocity time graph, the velocity is going to abruptly go to 0 until we reach 7 seconds. And then at 7 seconds, the graph changes again, and we now have a slope. It goes from 7 to -3 in 2 seconds. So that's a velocity of -10 over 2, which is -5. So the velocity becomes steady, again, at a value of -5 for 2 seconds. So this is the velocity time graph corresponding to the same motion. Okay? And the lesson here is that it is incredibly important to read the axes. Okay? This is a velocity time graph, not a position time graph. So the velocity time graph representing motion looks completely different from the position time graph representing the motion. So if you don't read the axes and you don't look, what kind of graph am I looking at, you are going to be completely confused. Okay? I cannot stress that enough. As I said, today's lesson is about slope. So what does the slope mean for a velocity time graph? Okay? Slope is change in vertical axis over change in horizontal axis. The horizontal axis is time. What's on the vertical axis is velocity. So the slope of a velocity time graph is equal to acceleration. So that's our third key fact for today, is that acceleration is the slope of a velocity time graph. So there's 3 key facts for today. Slope of a position time graph is velocity. Slope of a velocity time graph is acceleration. And acceleration can also be represented as bendiness of a position time graph. So you have 3 key facts for today. So let's practice interpreting velocity time graphs. Okay, so I've got a velocity time graph here. Okay, let me just draw it out. So this graph has 3 segments. It has segment 1, which goes from here to here. It has segment 2, which goes from here to here. It has a single point, which I'll call point 3. And then it has segment 4, which is right here. And so we want to describe what is happening in each segment. Okay? So when I mean describe what is happening, I mean give a direction of travel. Which way is it headed? Is it headed in the positive direction or the negative direction? Or is it at rest? So you have 3 options for the direction of travel. Is it moving forward, backward, or at rest? And then also you have to talk about whether it's speeding up, slowing down, or constant velocity. Okay? So and we're going to talk more about velocity time graphs next week, so you don't have to master this immediately. But let's talk about what's happening in segment 1. Well, in segment 1, here's the time axis right here, and we're above that. So that corresponds to positive velocities. So in segment 1, if your velocity is positive, that means you are moving forward. Forward meaning in the positive direction, whatever that means in the context of this situation. So moving forward could mean going upward, it could mean going to the right. What's happening to the velocity? Well, the velocity is steady at whatever value this is. So this is moving forward at a constant speed. That's what's happening in the first segment. Okay? Let's talk about the second segment. For the second segment, we can see that we're still above the time axis. Our velocity is still positive. So that means that we are still moving forward. But if we look at the velocity, it is approaching smaller and smaller numbers. It's approaching 0. So we would say that it is moving forward, but it is slowing. Slowing down. That's what's happening in segment 2. In segment 3, okay, segment 3 is just an instant. It's just this point right here. And we can see that in segment 3, the velocity is 0. So that means it is at rest. It is momentarily at rest. Just for an instant. Segment 4. I'm going to let you guys type it in. Type in what is happening in segment 4. So is it going forward, backward, or at rest? And is it speeding up, slowing down, or constant velocity? Okay, type it into the live chat if you know, while I write some more graphs. Okay, so first key point is that the velocity is now below the time axis. So you are moving backwards, okay? So you're moving back. And what's happening to the speed? So this is a little bit tricky. If you have a speed of -5 or a velocity of -5 meters per second, and you have a velocity of -10 meters per second, a velocity of -10 is faster than a velocity of -5. Okay? So kind of like how far away from the time axis is your speed? All right? Um, a velocity of plus 20 meters per second is slower than a velocity of minus 30 meters per second. A velocity of plus 20 means you're going 20 meters per second in the positive direction. A velocity of minus 30 means you're going 30 meters per second in the opposite direction, okay? So what we can see is that the velocity is moving away from zero to more and more negative numbers. So it's actually getting faster. So you could say speeding up. That's what's happening there. Okay? And like I said, you don't have to master this interpretation immediately. We're going to work on this for the next lesson as well. All right, so what I have here, if I could direct your attention to the bottom left of the page, is what I have here is two graphs that look superficially the same. What if I cover up what's on the vertical axis? Okay, these graphs look exactly the same. They're just a flat line that is below the time axis. Okay, but the interpretation is completely different because this graph is a position time graph and this graph is a velocity time graph. All right, so this example is going to illustrate why it is crucial to read the axes. So what's happening in this first graph? Well, the position number is just remaining constant. So this graph represents being at rest at some negative position, okay? So maybe x equals minus 3 meters. It means you're at rest at some negative position. This graph, your velocity is negative. So that means you are actually moving in the negative direction. What does it mean for this graph to be flat? Well, the fact that it's flat just represents that the velocity is not changing. So here, this second graph means you are moving back at a constant speed. Okay? So the graphs superficially on the surface look the same, but when we read the axes, they actually represent completely different things. Okay? So that's my lesson for today. We're going to talk more about the velocity time graphs tomorrow. Or not tomorrow, but whenever I see you next Tuesday, I guess. So that's my lesson, and I will meet you in the Zoom room in about a minute. Okay? See you soon.